Okay, last talk of this session, we have Andrew Jones from Ventana.
Yeah. So thanks a lot for sticking around for this, I guess, last demo of the demo theater for a while. This is actually going to be a demo. So you'll get to see lots of text and numbers go by. It'll be fun. This is about device assignment with the RISC-V IOMMU. So before those numbers and text go by, I want to make sure I describe the configuration for the demo, so it's understood what we're looking at. And we'll start from the bottom up here. So the platform, in this case, is just going to be QEMU, RISC-V board. And it already has these E1000E Intel interrupt controller, network adapter models in there that we're going to use. There's also, in this particular QEMU version, there's an IOMMU model that hasn't been upstreamed yet, but it's in progress right now. It already is support for the advanced interrupt architecture interrupt controller, which is RISC-V AIA. And so on top of that platform, we're going to boot Linux as usual, which includes the AIA driver, which has been recently upstreamed, including support for KVM to be able to launch guests with AIA as well. And there's also an IOMMU driver in there, which is currently being worked and posted on the mailing list as we speak. So it's progressing to be merged, hopefully very soon. Of course, Linux also includes KVM and VFIO, which are needed for this demo as well. Because we're going to be launching KVM VMs, which are finally at the top of this, diagram. And since this is a device assignment demo, over on the right, I've pointed out what we're trying to actually do. We're assigning these E1000E network adapters to these respective VMs, 1 and 2. OK, so I keep saying the term device assignment over and over again to make sure we're all on the same page for that. On the left was no device assignment. A virtual machine is running. It still uses I/O. It needs to do something, but it's actually not accessing the hardware directly. The hypervisor is in between. It's using emulation, trap and emulate, or parvert devices in order to provide that I/O. Now, with device assignment, we're actually able to access the device directly from the VM. Thanks to the IOMMU, we can avoid allowing the VM to program the device to DMA wherever it wants and cause all sorts of havoc. And that's for the DMAs. But if we also want to be able to have nearly full pass-through of this device to the VM, then we also want to make sure the interrupts are going directly into the VMs. So on the left side here, again, this is the less optimized version. This is the one with no irqbypass, where, OK, the DMAs are actually directly, but the IRQs are still going to get intercepted by the hypervisor. It's going to say, aha, this is actually meant for the VM, and it's going to do interrupt injection. Whereas, if the hardware supports it, and the RISC-V IOMMU and RISC-V AIA specifications have made sure to support this, we can actually do irqbypass, where the device can be programmed to write to its guest interrupt controller, and it will actually go directly into a VCPU without the hypervisor being involved. All right. I promised we would do the demo, and we will. But before we get there, I want to make sure that there's a few aspects of this irqbypass stuff that we need to all be on the same page for as well. So first of all, we're talking about MSIs here for the interrupts. Okay, so we're going to be passing message signal interrupts. And so we have MSIC in RISC-V talk for the MSI interrupt controller. And the VCPU has a virtual one. That's what the little V there stands for. And so when you want to program your device to send MSIs for events, you're going to give it the address of this S-mode file, which is this base address of the MSIC. And it's going to write into there the MSI, and then you get your interrupt. But since that's just a virtual a VCPU, just virtual, it actually needs to go to real hardware somehow. And so that's where the AIA, RISC-V AIA specification has really helped out for this type of use case. Not only does a heart, a RISC-V heart, have the S mode file for being able to have the host be able to have MSIs raised. But it also has a whole bunch of these guest ones, VS mode files. And it can have plenty of them. And we can actually map VCPUs directly to those. And so when we do the irqbypass, or when we want to have an interrupt go directly into a VCPU, we make sure that we configure, this is the hypervisor doing the configuration, in our case KVM, that it is bound to one of these VS mode files. Now you might already be thinking, well, what happens if I decide to move my VCPU to another heart? And well, yeah, you would be right to be concerned about that, because we need to make sure we migrate it completely, right? We need to kill off that binding from the old heart that we were bound to originally, and now that we migrated to another heart, we point to a completely new VS file there. So we do that. And we're not done yet. This is the last slide, I promise. Because there's yet another mode of operation here. What you may have already also been thinking to yourself, well, you know, there's a lot of those VS mode files, but they're not infinite, right? So what happens if I have more VCPUs than I have VS mode files? Well, you're right. You wouldn't be able to run that VCPU. Or, in this case, what the RISC-V AIA, again, considered, was that you could actually have this ability to write the MSI to a file. So we call them MRIFs, so memory resident interrupt files. And now the hypervisor has to be involved, right? Because now you've just written it to memory, and it's like, OK, it's just going to sit there, and nobody's going to know about it. So the hypervisor is aware when something gets written to an MRIF, and it injects, or it forces the VCPU to loop and see that. So, and also all accesses now are back to trap and emulate when that's in mode, when that mode is in being used. OK, so text and numbers, because that's what software really is, right? We'll come back to that. There you go. So this demo is going to be just as if I was typing it, and because I did this morning. But I did record it because, you know, I might be a wild guy, but I'm not that crazy, really. So, all right. So for starters, I'm just showing the QEMU command line. This represents what we talked about in the first slide for how the platform was built. And now here, the host that we boot, that Linux host, has already been boot up. And I'm just showing that, yeah, indeed, we have those two E1000Es I was talking about. They're there. In this case, they've already been activated. They both have two different networks, right? Only one number different, but you can see that one's on the 0 subnet, the other on the 200. So without further ado, we can look at the VMs now and get them involved. So there's two of them, as we said we would do. For starters, let's just look at one. So we kick that off, and the moment we kick it off, VFIO got engaged, did its thing, it unbounded from the host and bound it to the guest, and now we can see it disappeared from our listing there, right? So now it's part of the guest, been assigned. All right. So here I just show that I get it set up. I'm even a slow typer when I'm recorded. Sorry about that. And we see that it's working. But so far, all this is great, but we actually haven't really proven there's an IOMMU there at all, right? Let alone irqbypass. It's just like, hey, cool, and it works. But so we'll get to that. So here I'm just showing that we're getting interrupts. If you look at the east 0 lines there, kind of in the middle, you see over on the left side that there's non-zero values there, which means that we're getting interrupts, right? And in fact, the receive channel is going to continually getting some periodic interrupts, which is good for this demonstration because I want to show that translation of those MSIs. So that's what we'll do now. And we can do that easily because our platform is QEMU by just enabling some trace. So enable trace for MSIs. This is the IOMMU doing these translations. So these numbers are very similar, which makes it extra fun to look at. But if you look on the left side of these numbers, where the 28 all zeros, this is actually what the guest is considering its IMSIC address to be. This is where the MSIs are being delivered as the guest programmed the device to put them there, because that's what the guest believes is the right place. Of course, that's just virtual. It looks similar to the ones on the host only because both the host and the guest are using the same virtual machine model. But they are different because on the host side, the right side there, you see that it's some page offset actually off that base address. And those are actually the offsets into those guest interrupt files we showed a few slides ago. And so you can see that when an MSI is being triggered by the device, first it's writing to that guest address, that left side of the arrow, and then the IOMMU is translating it into the guest interrupt file, which is on the right side of the arrow, and it's getting injected directly into the VCPU with no hypervisor involvement. So irqbypass doing its thing. Now, hold on to your hats. I'm going to make a bigger mess of the screen because I just want to show that the DMAs are being translated as well. So we'll first enable DMA tracing, and then with adding ping in there, we start making some packets. And you can see a mix now of these MSI trace with the DMA trace. And indeed, we have these types of things I already pointed out, which are the MSIs going where they belong. And now we also have these guys, which are, these are the physical addresses, what the guest believes, guest physical addresses, and this is the host physical addresses. So we've proven that IOMMU is doing everything we said it should. And so I shut all that off now before the screen gets too crazy. I think I scrolled back here in case I forgot to pause it. So this is the same information, just in case. OK, but we also said, what about migration? So with migration, we would expect these traces to have the same address on the left-hand side, the guest addresses, but on the which is what we see there. And on the right-hand side, we're going to see those host addresses again, but we would expect them to be changing because we're migrating the VCPUs. And so we're going to different guest interrupt files on different actual hearts. And in fact, we can see that now because I've started a script which is doing a task set over and over again and mucking up the normal business of Linux to make sure that we force that. And you can see over here, indeed, we're cycling through different guest interrupt files. OK, so now we've exhibited so far everything except for those MRIFs. And so now VM2, which was sitting there unused so far, is a special VM. I made sure it's going to use MRIFs. So I had to kind of hack stuff to force that because we have those guest interrupt files there, and KVM would prefer to use those. But so forcing this VM to use MRIFs, everything should look identical except for those translations. And so that's what we're going to see as my slow typing catches up with my faster speaking. So yeah, we see everything same so far, working as the other VM was working. No differences at all. Now we're going to enable trace though again. And we're going to see, yeah. So now we see these are host physical addresses where the MRIF is, right? So no longer are we going directly into a guest interrupt file, which is some offset off of that 28 hex number, but actually into some random looking address, which is a host memory page. And now here I throw on another trace. This is the MRIF notifications. Because as I said, I mean, if you write to a memory address that you have an interrupt, nobody notices, nobody's going to care. And it won't actually get delivered to the guest. So what the IOMMU, RISC-V IOMMU, has specified as it prepared for irqbypass is that when you write to one of these MRIF files, it goes, aha, that was an MRIF. It wasn't actually going to get delivered directly. So it raises a notice MSI itself. And that notice MSI will then be what KVM can use in order to ensure that the guest is aware of that. And that's actually it for the demo. There's a little bit more here where I just show that they actually work in harmony together, but you've already seen all of the important bits. So I can.
Oh, thank you very much. The sessions are just starting just now, but I think if anybody has a question, they can come up to you.
Yeah. So I actually have a poster tomorrow, and it's on the same topic. So I'll be like lurking there from time to time, and if you have questions about this, I can knob it. This is pointing you to the GitHub where I have the POC code for all that IRQ bypass stuff.
Thank you very much.
Yeah.